Okay, well, good afternoon, everyone, and thank you, Peter, for that introduction. Can everyone hear me in the back? Okay, 5. Okay, so as Peter said, I'm from Goddard Space Flight Center. How many of you here are familiar with NASA? Okay, that was a trick question. But what about Goddard? Does anyone know about NASA's Goddard Space Flight Center? A few of you. But so I'll start off by introducing, what are the different centers within NASA? What does Goddard do? Goddard, by the way, is named after Robert Goddard. He's called the pioneer of rocketry. He invented rocket engines early in the 40s and 30s, and so we're named, the center I work in is named after Robert Goddard. So we're one of the 9 field centers of NASA. You might have heard of centers like Kennedy Space Center, from where we launch resupply missions and a number of other missions. Johnson in Houston. We have Stennis, Glenn. These are all field centers across the United States. So Goddard is on the East Coast, very close to Washington, D.C., and that's where I work. And I manage, within Goddard, our internal research and development program. So this is a program that invests in technology development, technologies that will, at some point, be converted into instruments, detectors, new ways of exploring the universe, new ways of looking down at Earth, and giving us information that we do not have. So that seed funding is what my program does, to invest in these technologies that are 100% strategically aligned with where NASA wants to go in the next 5, 10, 15 years. So that's a little bit about my job. My talk says role of standards, but the way I will come to standards is from the different missions that we do. So I'll try to create that link between the variety of missions that we do, and then what is the role standards, such as the IPC standards, what is the role that these standards play in us enabling these missions. So Goddard, as I said, is close to Washington, D.C., but it itself is composed of many different smaller sites. We're quite unique in a number of different perspectives. One of them is our ability to create a concept, a technology concept, mature that concept, build the hardware on center, and then fly it as well. So we're quite unique in that way because we manage the Wallops flight facility. That's one of our sister sites, about 200 miles east of where we are. So we can go from the drawing board to low Earth orbit within the center. So that's unique. But we also manage about 98% of traffic, of network traffic from the International Space Station and from many other assets in low Earth orbit and in geosynchronous orbit. So 98% of that traffic, network traffic, is managed through Goddard's infrastructure, both in Maryland, where I am, and also in White Sands test facility, which is in New Mexico. That's where we have the large radars that are constantly talking to some of the assets. We also run an IV&V facility in the state of West Virginia, and we have also a balloon facility, out of which we fly ultra-long duration balloons, weather balloons, or other astrophysics instruments are flown on those balloons. So that combined is what NASA Goddard Space Flight Center is. Now, I mentioned earlier about exploration and astrophysics. So we look at our technology development in 4 key science areas. And these key science areas are astrophysics, which is really looking out into the universe, looking at phenomena such as black holes, answering big questions such as, are we alone in the universe? So we're developing those concepts. The James Webb Space Telescope that launched in 2021 was conceptualized and built partly at Goddard before it was sent to our partner site in California and then flown out of French Guiana. So that was our big astrophysics mission. We're looking into future missions to look into habitable worlds. Are there planets that have atmosphere and conditions ready for or available to sustain life. So we're working on next mission concepts within astrophysics to answer those questions. Are there other habitable worlds out there? Our second science line of business is heliophysics, which is understanding the effects of sun here on Earth. How do coronal mass ejections travel from the sun to our upper atmosphere? Once the coronal mass ejections reach our upper atmosphere, how do they affect communication here on Earth, terrestrial communication, cellular communication? How do those energetic particles change the density of the atmosphere? And that in turn changes the space weather. That governs how we would fuel up a spacecraft. Depending on the density through which this spacecraft is going to travel, the fueling of that spacecraft and the trajectory is designed. So those are some direct applications of heliophysics, understanding the sun's impact on Earth. So Goddard is one of the world leaders in that science, in heliophysics. Our next science line of business is planetary. So this looks at planets other than our own within the solar system to explore and find out what types of other forms of life might exist in moons such as Enceladus, which is one of the moons of Saturn, but also closer to Earth, looking at our own moon. We're developing instruments today that will help us understand what does the lunar soil, what is the composition of the lunar soil? Can we develop autonomous rovers and robots that can go land on the moon one day and do this analysis and then communicate that data back to us so we can better understand what is the composition of the lunar regolith? So that's planetary. And then the fourth line of business is the earth science line of business, which is using the vantage point of space to look down on Earth and seeing how our planet is changing, how it is evolving. And we're collecting various pieces of information about our planet, including ocean surface temperature, ice cover, greenhouse gas emissions, and many other discrete science signals to combine all of those to create what we call an Earth System Hub. That's one of our projects that we're funding currently, which is to understand all of these discrete symbols to collectively look at the effects of both human man-made factors and external factors on our changing climate. So those are our four key science areas. And within these science areas, we invest in technology developments, these instruments that help us get this data about coronal mass ejections or about ocean surface temperature, plankton content in the ocean. These begin as ideas from engineers and technologists who will then receive funding from my program to take that idea through a maturity stage to create that mature idea, which will then one day fly on a spacecraft. Now, what is enabling these different science disciplines are our engineering and technology workforce. So the last presentation we heard from Nokia was quite interesting. I was listening to it very attentively because one of our lines of business, the communication and navigation line of business, is doing exactly that. We're getting ready to create the infrastructure to go explore the moon. Now imagine I mentioned robots and rovers on the lunar surface. All of these robots and rovers have to communicate with each other, and they have to communicate back here in close to real time. So for that, we're creating what we call the LunaNet, which is a lunar network, which is a close to 5G experience for these autonomous systems to make autonomous decisions, generate the science data, spectroscopy, soil analysis, and then convey that data back here on Earth. We're creating the infrastructure for LunaNet, but also a GPS type of an environment. There is no GPS on the moon today, but we want to have, if we want to have these explorers go out and do their stuff, we want to make sure they know which way they're going. So that is communication and navigation. Some other engineering disciplines include our cross-cutting technology line of business, where we look at other mission concepts such as distributed missions. What does distributed missions mean? So today, if you look at a certain satellite or spacecraft, it is a single spacecraft which has multiple instruments. The concept that we are exploring is having a constellation, a smaller constellation of spacecrafts that can be combined or detached from each other and do different types of sciences. So it's like a science on demand type of a concept. So we call that distributed science missions, DSMs. So imagine, let's say, a wildfire in a certain part of the country. Our concept with the DSM would be to have these spacecraft do the initial observation and then on demand create a constellation on top of where the wildfire is so we can provide that first response. Or imagine another scenario on the moon of Enceladus. Some of you might have heard about last 2 months ago, there was a hot or a geyser, a sprout of water that was observed on the moon of Saturn called Enceladus. So this is a science event where we would like to go in and grab some data to see what is the composition of that material coming out of the surface of that moon, how hot it is, how high is it going, and what is the source. So the DSM type of architecture will allow us to reposition the satellites on demand in response to that event. So that's the concept of DSM. But we're also looking at other sensors where the limits of classical physics are being reached. So today, gravitational waves are beyond the measurement. They are so faint, these waves are so faint that they're beyond the measurement capacity of traditional sensors. Classical physics cannot measure those gravitational waves. So we're looking into quantum technologies. We're investing heavily into quantum-based sensors so we can study these waves both here on Earth but also out in the universe in greater detail. And all of that needs technology investments and technology developments. Today, if you look at a quantum gravity gradiometer and a QGG, it's about the size of this stage. And what we're trying to do is make it smaller and more efficient so we can put it in a smaller form factor and fly it. So that's our investments in quantum. And along with these, of course, we try to invest in artificial intelligence because that has a number of applications, direct and indirect for us. Artificial intelligence can help us with the DSM architecture I just described. If we have onboard intelligence on a spacecraft, these spacecrafts can talk to each other and do the science on demand rather than having a long connectivity from Earth. So rather than scientists commanding these spacecrafts to do certain things, these onboard intelligent processors based on AI can do those autonomous decisions. So for that reason, we're looking at AI. And of course, in that whole process and the whole mix are other digital engineering efforts that we're also investing in. So hopefully that gives you a kind of a broad picture of the types of investments in science and engineering that Goddard is making. I mentioned we're supporting a number of exploration activities for the moon. That is part of the Artemis program. Has anyone here heard about the Artemis program? Some of you. Artemis from Greek mythology was a sister of Apollo. So as you know, we had the Apollo program back in the 70s. So as a logical sequence, the next step, we're quite active in supporting various components of the Artemis program. I mentioned autonomy is one of them. Lunar search and rescue. When, and not if, but when our astronauts go back to the moon, they will need GPS, they will need the infrastructure to communicate and navigate on the lunar surface. And they'll also need search and rescue, so that if astronauts or these explorers need to know the direction in which they need to go, they'll have the search and rescue. And then, of course, through our space weather and heliophysics contributions, we will be able to better provide or predict coronal mass type events that are headed to the moon so that these explorers can take protective measures at the right time. So these are some of the ways in which we're helping with the Artemis program at NASA Goddard. Now, I mentioned a few things in which Goddard is unique. It is unique in one other way, which is it is the largest collective of scientists and engineers in one campus throughout the US. So we're about 10,000 big scientists and engineers and technologists and other support functions working together to achieve these science and exploration goals. So out of these 10,000 people, about 3,000 of them are civil servants, such as myself, but we have a big contingent of visiting scholars and researchers, not just from the US, but from around the world. And then we have a number of contractors, support contractors that also support our work at Goddard. This is a quick look at a manifest for the next 4 or so years. Just last Sunday, before I flew here, we had a very successful recapture or return of the samples from the asteroid Bhanu. Some of you might have tracked it. This is a mission that we launched out of Goddard in 2016. The mission was to have the spacecraft called OSIRIS-REx grab a sample from an asteroid and return it back. Big deal. Imagine going 1.5 billion miles out, landing, actually touch and go. The concept is tag, touch and go type of a sample acquisition, and then bringing it back another 1.5 billion miles back, and then precisely delivering it within a 27-mile ellipse in the Utah deserts. So we did that. We did that last Sunday. So we're now doing exploration of those samples, which are about, I'd say, a few hundred grams. But that'll tell us a lot about how the solar system started, how it evolved, because that asteroid has a lot of organic components in it. Organic meaning carbon containing. So that's what happened last Sunday. But we also recently launched the CRISM satellite. This is an X-ray observatory. This is in collaboration with the Japanese agency called JAXA. This was already launched. And we also launched the last resupply mission, the 19th resupply mission from a Goddard site to the International Space Station. So as I mentioned earlier, Wallops is one of our launch facilities. So we regularly send food, water, science experiments to the International Space Station from our facility. But we have a busy few years coming up. We have our plankton aerosol mission coming up, PACE. It's going to study the amount of plankton in the oceans. We have a weather prediction satellite. We have some solar weather prediction satellites. This one is interesting, the capture, containment, and return system. This is the Mars sample return. Just like we returned the sample from the asteroid, Bhanu, this satellite, this mission going to launch somewhere in 2026 is going to bring us back samples for the first time from Mars. So that's 2026, and then we have our next space telescope called the Roman Space Telescope, scheduled to launch in the same year as is the Joint Polar Survey satellite. It's another weather prediction satellite. So that's a future few years for the large satellites. But in between all of these, we fly a number of smaller satellites. And that's kind of leading to the next kind of phase of my talk, which is what types of missions do we fly? Of course, we fly these very expensive, long lead time missions that take us decades to develop and build. But we also fly a number of smaller satellites. These are sometimes called small sats or CubeSats. Is anyone familiar with the word CubeSat? Some of you are. CubeSats are literally like that, a 10 centimeter by 10 centimeter by 10 centimeter cube that is flown in low Earth orbit or beyond. So you can have a 6U cube, that means 60 centimeters by 10 by 10, and we fly a lot more of those. We do not take 15 years or $1 billion to build those. Those are quick turnaround missions with a specific science objective, and more importantly, we're allowed to take more risks during the development of these smaller turnaround, quick turnaround missions called CubeSats. And so, but as you can see here, it's a busy page, but it gives you an idea of the types of missions. James Webb Space Telescope is here. The OSIRIS-REx is right here, shown with the asteroid. These are some of the missions for heliophysics, and these are the Earth missions. But risk becomes the central theme in this spacecraft development work that we do. Because risk is what drives a number of requirements. It drives a number of engineering practices within our organization. Certain missions, such as the ones shown close to Class A, are low risk tolerant by design. So the James Webb Space Telescope, for example, is a great example of a Class A mission where the risk appetite is extremely low. Any and all risks have to be identified on the ground and then addressed and brought down through testing, through additional analysis, so that at the time of launch, we're carrying as few risks as possible. That means a small risk appetite. That's a Class A mission. You contrast that or compare that with a Class D mission, which we have on this side here. We fly a whole lot of Class D missions. So there, we are allowed and we are required to take more risks in order to shorten that technology development timeline, in order to meet our strict cost and schedule guidelines. So here, we can take more risks on this side of the chart for a Class D mission. Now, what does that mean from a standards perspective, right? What does risk have to do with how we flow down or identify our standards? Because eventually, we're talking about hardware risk. We're talking about how do we buy down that mission risk through technology and hardware. So where is the connection? So once we start identifying that risk, A, B, C, D, that becomes a central theme that drives not just our engineering practices or how we would do our scheduling or parts or testing, but also drives our finance, our testing, systems engineering, and the science team. So that becomes a central theme. Now, the reason we worry about risk, well, what is risk, right? So we talk about, this is too risky or this is low risk. Well, what is risk? So at NASA, we have a specific definition of risk. And we arrive at a risk, we calculate a risk based on two factors, a probability and a consequence. So what does that mean? So risk is the expectation of loss in statistical terms. If you invest in the stock market, you have a certain expectation of loss. Well, what is the risk? Well, it is a combination of two factors. What is the consequence of that loss? And what is the probability of that loss? Those are two different things and on two different axes. It is only when we've identified both of those can we say, well, we've identified a risk. And in our work and in many other organizations, risk is identified and then communicated through a fever chart. Here you can see likelihood is on one scale and the consequence is on the other scale. Because as you can imagine, in an engineering world, in electronics manufacturing, certain failures can be extremely low probability. Think about some projects that you're working on today. They may be very low probability failures, but the consequence could be very, very high, right? So you would put that likelihood on 1, but the consequence could be 5. So that would be a 1 by 5 risk. Now that's in the yellow. And that tells us what steps should we take. If we're a Class D mission, the very low on the scale, should we be addressing this remote possibility of failure, or should we accept that risk and move along? It's usually the latter. We accept that risk, we document that risk, and we move along. That means when we launch that mission, we understand that there is a list of risks that we've taken during the development process. We've understood these well, and we also know what is the consequence of these risks. So that's a little bit about risks. And we define risks as technical risks, safety risks, or programmatic risks. A risk can be a cost risk or a schedule risk. So that falls under programmatic. Now, why do we worry about risk? Of course, we don't want bad things to happen. But on the flip side, quite often there are organizations, including mine, where we arrive at a risk just by doing guesswork or brainstorming. Let's say I have a piece of hardware, and a group of experts sit down and they say, well, here are the 20 ways in 20 failure mechanisms that will affect this particular hardware. But that is not risk. that is just a product of experience, that is a product of brainstorming? Should we be acting on all these 20 failure mechanisms? Let's say in your product there is corrosion, there's going to be high humidity, there's going to be fatigue, there's going to be creep, maybe some connector corrosion is going to happen. These are all possibilities. These are not risks. It is only after we identify what is the probability of each of those failure mechanisms and the consequence of those failure mechanisms, we start to identify risks. And so quite often, we start taking actions, including in my organization and many other organizations I work with. The actions are driven by just the probabilities or just the consequences, not the probabilities. And that is usually always results in some type of a risk with either cost or schedule. They've gone into a rabbit hole, and they're now addressing a certain failure mechanism that has a very, very low probability, and they've now spent 7 weeks and X number of dollars addressing that failure mechanism. So to bring that in context. Now, some of you may be familiar with a certain type of bed called a water bed. It's a mattress. So I like to show this because it's a good illustration of unbalanced risk, where you, in some cases, if you press on that risk or you press on that water bed in one side, it starts to rise on the other side. What that means in a program you might be working on or you might be developing, if you start devoting extreme amount of resources to address one low probability event, you are bound to increase the risk somewhere else in that program, either today or a month from now or a year from now. So the idea here is to try to maintain a level waterbed of risks by understanding what these risks are, by documenting them and prioritizing these risks. So changing gears a little bit, and before I introduce the standards, these are some of the technologies we're working on. I talked about autonomous processing using AI, autonomous navigation for DSMs, onboard decision making for resilient spacecraft, so spacecrafts that can do self-healing, something else that we're also working on. The Climate Science Hub, which is a collection of instruments and assimilation of data for evolving climate science needs. So these are the examples of different technologies we're working on. This gentleman here, he's holding a terahertz receiver that will be one day be used to detect water on the lunar surface. So that terahertz receiver is going to be packaged in a small form factor. It's going to sit on the side of a rover, and it's going to go around and detect water molecules on the lunar surface. So these are some of the technologies that we're developing today, but we're also keeping an eye on the new generation of technology needs. Quantum technologies, quantum sensors, quantum communications, AI and machine learning, we're quite heavily investing in those. Integrated photonics, this is the integration of optical components with electronic components, creating photonic integrated circuits, or PICs. So that will help us achieve faster transceivers that can, you can fit those on the palm of your hand and still get 50 to 100 gigabit per second type of speeds. These would be vital in developing technologies around LiDARs. These would be vital in other communication technologies. And then, of course, 3D printing and 3D manufacturing is another one of our investments where we're looking at circuits using 3D printing. But all of these systems are complex. They each involve many different parts, many different components that have to come together, work together, be tested together before they're flown. And each of these different components have their own failure mechanisms. The dies have their own failure mechanisms, the solder joints, the circuit boards, individual vias have different failure mechanisms, batteries, solar panels. So it's a collection of different failure mechanisms that we have to identify, prioritize from a risk perspective. And it's important in this context to define what our quality requirements should be as we define these missions, as we define how we're going to build these. The quality, we're all familiar with quality. What is an acceptable quality based on certain requirements? It's the totality of features and characteristics of a product that bear on its ability to satisfy given needs. It's very different from a reliability. The reliability of a product is its ability to perform a function within the expected life cycle conditions for a certain period of time or for a certain number of cycles. Very different. Now, the context here is what I'd like to call misguided quality. It's defined by specifications that have no linkage whatsoever to the end item reliability. There's a requirement that just exists, and it sits there, and we have to check the box. We have to check the box, but it comes at an expense of either cost or schedule. And that's misguided quality. And as technology evolves, as we start using newer ways of identifying failure modes and mechanisms, it's quite critical to identify where are these misguided quality factors and what can we or what should we be doing about these misguided quality factors. And there's also the tendency to do upfront reliability assessment. And we do this a lot, where we would create failure modes and mechanisms on the piece part level. We look at all the mechanisms that affect a circuit board. We look at all the mechanisms that affect a solder joint and the components and the passive parts and the active parts. But now what happens when we bring all of these together? This now becomes a system of systems. And you put in more variability with supply chains, testing, and other environments that we're not aware of. It becomes quite complicated. So the point here is there are certain uncertainties, including in supply chain, that can negate the effects of this upfront reliability assessment. So the drive, the priority that we have is to start looking at systems as opposed to individual component level reliability assessment. And for that, we're using digital engineering, model-based approaches where we can take FEA data, we can take other analysis data, and roll that up into a larger system level analysis so that we can do response surface modeling, we can do sensitivity analysis in a virtual manner without creating test samples to test that out. So that's a big driver that comes from this. Now, from a standards perspective, we use IPC standards for our printed circuit boards, for our solder joint evaluations, but we also use mil specs, and we use ESA specs, the European Space Agency specifications. And sometimes we also use specifications that are developed in-house by our contractors. So let's say we work with Lockheed Martin, they might have an internal printed circuit board specification. Let's say we work with MIT's Lincoln Labs, they might have an internal printed circuit board specification. So we use a combination of all of these standards for defining our requirements and for assuring quality compliance. But we also understand that these standards are just the first step in defining reliability, because acceptable quality does not mean acceptable reliability. There's a key difference there, as I mentioned earlier. This is an example of a board that we've built, designed in-house at Goddard. It is called our Space Cube Mini, and it comes in two versions. It's a 3U. Remember the CubeSat, 1U, 2U, 3U. So that's the dimensions of that board, and it also is available in a 1U. So it's supposed to be this modular architecture board that is developed in-house at Goddard to allow for different types of processing, onboard data processing approaches. Now, we used IPC specifications. Yeah, sorry about that. Looks like some interference. So we used an IPC specification to develop and manufacture this board. But what we found was sometimes when we used the space addendum requirements, the number of iterations it took us to successfully fabricate this board increased. So the point here is when we look at the space addendum requirements for fabricating a single board computer such as this one, we found that there were a number of bottlenecks in the standards that allowed us to not successfully meet the requirements in the space addendum. And what were the specific items that we found issues with? Well, we had issues with via pad size, spacings, the amount of the copper thickness requirements for a certain current carrying capacity, the spacing between a ground plane and a power plane. What that did was it complicated the design. It also increased our layer count, and it also increased the number of vias that we needed to drill into that single board computer. In the previous slide, I gave you an idea of the perspective, the size of this board. It's a 10 centimeter by 22 centimeter square board, and in one case, it's a 10 centimeter by 10 centimeter single board computer. So the only way we can go is up in thickness, but the space addendum requirements caused additional complications. So the point that I'm making here is, as intelligent users of these standards, we identify some of these bottlenecks and we take them back to our committees. We take them back to the 6012 committee, the 610 committee, the 600 committees, and tell them that, hey, this standard, the way it's written, is not going to enable us to build the next generation CubeSat. And here are the reasons why. So let's put our heads together and see how we need to update the standards so that they can allow us to repeatedly make these single board computers. And so that's the point with the SpaceCube Mini example. But we consistently and constantly keep an eye on our materials, or our printed circuit board materials. And the slide I'm showing you here is an evaluation that we did of about 600 bare boards, 600 different designs over the course of a few years. And we saw out of these 600 or so unique designs, as they were taken through the various microsectioning and other lab processes, we found close to 250 non-conformances. It means 1/3 of the boards that we saw in a 3-year period were non-conforming. What was causing these non-conformances? Now remember, non-conformances does not mean failure. Non-conformance means it does not meet the spec. So we investigated this a little bit deeper, and we found, well, we looked at our top 10 suppliers for printed circuit boards, and we found that amongst the top 10 suppliers in these 638 unique designs, this was the spread. So the blue line is the submission rate. So supplier number 1 had about 1/4 of those submissions, so about 150 of those designs came from this supplier, and the orange lines shows you the non-conformance rate. So out of those 250 non-conformances, how many non-conformances did that particular supplier have? So we found that certain suppliers, even though they're submitting a smaller number of boards to us, they have an enormous amount of non-conformances. So what does that mean? Should we stop working with that supplier? Well, it means something else. It tells us that perhaps we need to do a better job in matching the supplier's capabilities, their maturity levels with a certain design, with our designs. We need to do a better job with front-end engineering. That's what that tells us. But it also tells us some other things, which is, what are these non-conformances that we're seeing over and over again? So we looked at that data across the 10 suppliers, and we codified these. So A, B, C, D, for example, are these different non-conformances shown here. So we looked at the top 5 non-conformances from all of these different suppliers, and we found things like inner layer separations between plating layers, wicking, annular rings, and ENIGs. Those were our top 5 concerns. Now, you can look at those non-conformances and say, well, some of these can affect the reliability of the board. Some of these can actually cause certain failures that have a high consequence and a high probability. So these are actual risks. But in many other cases, we found that we could use the boards as is, because the non-conformances are such that they present absolutely no risk, or they present a very small amount of risk to that mission. So that is how we decide or disposition these non-conformances based on the picture of the overall risk classification of that mission. So when you look at these non-conformances, you're probably all very familiar with these. There are some issues with plating separations. There are some issues with wicking. Now, you look at this second one here, inclusion between plating layers. It can result in an intermittent open. Now, up until revision D of the 6012, how many of you are familiar with IPC 6012? Okay, a few of you. Well, that's the acceptability standard for rigid printed circuit boards. That's the one we commonly use for all our rigid boards. Now, as per IPC standard, up until revision D, that inclusion that you see over there was a non-conformance. I took it upon myself to do FEA analysis and physical testing to show that those inclusions have no effect or contribution on the overall reliability of a populated circuit board. We took that data to the committee, and in revision E, we changed that requirement. What that means is we have, based on data and analysis, we have effected a change in a standard, a requirement which was, in my previous term, I used misguided quality. It was a quality requirement that was a legacy requirement based on processes and chemicals and other things that were happening a decade or so ago, but it stayed in the standard. So we're able to influence the standards based on this data and real-life examples. And we've done that in a few other cases as well. So there is a case to be made here about the risk of a non-conformance versus the risk of a conformance. Very often, when we see non-conformances, we tend to send the board back to the supplier and tell them to refabricate that board. And the same can be true for an assembly or for any other product if it's non-conforming. What the hidden cost of that activity is that it adds cost and schedule to the development process for that particular product. It certainly does for us. It adds cost because now we have to get that thing fabricated again, but it also adds schedule. And schedule is king in our business. If we cannot meet the launch schedule, we cannot launch it. So those risks of conformance, making something conforming or forcing it to be conforming, can actually transfer into a programmatic risk for us. So we carefully balance out and evaluate, is it a risk of non-conformance, meaning use as is, or do we have to force it to be conforming, taking up that additional risk of cost and schedule? So in summary, standards play a key role in our development activities because they allow us to meet requirements, they allow us to set requirements, it allows for interoperability. That's essentially how we do all our business in manufacturing. But as technology continues to advance, we also see that there's a key need to continue to change and address these standards, to keep them updated. And that's the role a number of the committee members, some of you may be members here, are playing, which is to keep on top of these technology needs, seeing what these latest non-conformances are, bringing it back to the community so it's not just your organization, but the entire community can benefit from that learning. And of course, from a technology development perspective, partnering and collaboration is key. And we look for partners that will help us in our technology development efforts for different types of technologies, both electronics, circuit boards, parts, and others. So that is the end of my presentation. Thank you.